Welcome back to another explainer. Today, we're diving straight into the hidden, microscopic mechanics of electricity. We use electricity every single day, right? But the actual physics happening inside those wires is profoundly strange and, honestly, often completely misunderstood. So let's look past the plastic insulation and see what's really going on in there.
Okay, so picture this. You've probably noticed that the exact moment you flip a switch, bam, the lights come on instantly. But here's the crazy part. The electrons themselves, the physical particles actually carrying the charge, are moving incredibly slowly. So how can both of these things be true? Well, it all comes down to distinguishing between the super-fast signal of an electric field, which travels at nearly the speed of light, and the surprisingly sluggish physical reality of the electrons themselves. To wrap our heads around this, we're going to hit 5 key concepts today: the flow of charge, the slow electron drift, resistance and resistivity, power and heat, and finally, semiconductors and superconductors. Let's get into it. Starting off with part 1, the flow of charge. Think of electric current kind of like a rushing stream of water through a garden hose. Current, which we represent with the letter I, is just the total amount of charge passing a specific point over time. We measure that in amperes, or simply coulombs per second. But physicists also look at current density. That's basically how tightly packed that flow is through a specific cross-section of the wire. So, a wider wire, that means a lower current density, even if the total flow is exactly the same. But hey, for any of this flow to actually happen, something has to be pushing it. Enter the pump. To keep this steady flow going in a circuit, we need what physicists call an EMF device, like a massive battery array. It acts exactly like a charge pump. By doing work, it maintains a potential difference between its terminals, literally pushing those charge carriers through the circuit. No pump, no flow. It's that simple.
Moving right along to part 2, the slow electron drift.
This quote really hits the nail on the head regarding our opening paradox. The crucial point here is that the conduction electrons do not have to, quote, get anywhere. When that electric field is applied, the signal itself travels at nearly the speed of light. But the physical conduction electrons, they just slowly shift around within the lattice. They don't have to literally travel all the way from the power plant to your house to give you energy. They just kind of bump into their local neighbors. So just how slow are we talking? Well, in a typical copper wire carrying 17 milliamps of current, the electrons are creeping along at roughly 0.000000049 meters per second. Yeah, you heard that right. That is their agonizingly slow drift speed. To put that into perspective, at that rate, it would take a single electron over half an hour just to travel 1 millimeter. Crazy, right? Now, don't get me wrong, it's not like the electrons are just lazy. Inside the metal, individual electrons are actually ping-ponging around chaotically at something like 1.6 million meters per second, all thanks to quantum effects. But because this motion is totally random, they don't actually get anywhere. When you flip that light switch, the electric field just slightly biases their chaotic path. It nudges them to gradually drift forward at that literal snail's pace we just talked about. So where do these wandering electrons even come from? If you look at atomic models of isolated copper atoms, you've got these electron clouds. The innermost electrons are locked down tight to the nucleus, but when atoms group together to form solid copper, those outermost loosely held electrons, they completely detach from their parent atoms. They transform into these mobile conduction electrons that form a giant, shared, free-flowing sea throughout the solid structure. All right, part 3, resistance and resistivity. Okay, we need to clear up a super common point of confusion right now. Resistance and resistivity, they sound almost identical, but they describe entirely different things. Resistance is all about the specific object you built. It changes depending on how long or how wide that object is. Resistivity, on the other hand, is a fundamental property of the raw material itself, no matter what shape you mold it into. And we actually use these macroscopic components, called resistors, to put these properties to work in everyday life. Engineers specifically design these tiny components to strictly control the flow of charge, just by leveraging those macroscopic material properties. Those little colored bands on the outside, they tell you exactly how much resistance that specific component is going to provide to your circuit. Which brings us to a big one, Ohm's law. Now, a lot of people think the equation V equals IR is Ohm's law. Actually, scratch that. That's just the mathematical definition of resistance. The true essence of Ohm's law is that it's a physical property that is only true for certain materials. A material obeys Ohm's law if its resistivity stays perfectly constant no matter how hard you push the electrons. This happens in metals because the average time between all those microscopic electron collisions remains remarkably steady. Which leads us perfectly into part 4, power and heat. So every single time an electron drifts forward, it's almost immediately stopped by a collision with the atomic lattice. The electric field accelerates the electron, and then bam, it slams into an atom. All that kinetic energy provided by the battery gets continuously dumped right into the lattice, which makes the atoms vibrate faster and faster. This energy is irreversibly transferred into thermal energy. And you know what that means? That is exactly why your electronics get warm when you use them.
This transfer of thermal energy is what we call power dissipation. You calculate it simply as the current squared times the resistance. And here's the thing, this isn't just an annoying byproduct. Sometimes it's the whole point. This thermal energy dissipation is exactly what makes the coils in your toaster glow red hot to cook your breakfast, or what makes an incandescent light bulb shine brightly enough to light up your room.
And finally, part 5, semiconductors and superconductors. If you compare the materials here, the numbers are wild. Silicon has a vastly higher resistivity than copper. We're talking roughly 100 billion times more resistive. Why? Simply because it has billions of times fewer free charge carriers available to drift around. In fact, at room temperature, pure silicon acts almost exactly like an insulator, because its electrons are essentially locked in total gridlock. But engineers are clever, and they found a workaround. By carefully injecting minute amounts of specific impurities, a process known as doping, we can actually unlock silicon's gridlock. We can inject extra electrons or even create empty spaces called holes that act just like positive charges. This lets us command exactly when and how the material conducts electricity. And honestly, this single innovation of controlled resistance is what gave birth to the transistor, the microchip, and literally the entire modern computer age. Then, at the absolute extreme edges of physics, we find superconductors. When certain materials like mercury are cooled down near absolute zero, we're talking around 4 Kelvin, their resistance doesn't just get smaller, it literally drops to zero, completely. In this state, electrons flow freely, they never collide, and they never generate heat. They can drift forever without losing a single drop of energy. Which leaves us with a pretty provocative thought to wrap up today's explainer. We can already achieve zero resistance, sure, but only at impossibly cold, super expensive temperatures. So imagine a future where scientists finally unlock a material that superconducts at room temperature. A global power grid with absolute zero energy loss. Computers that literally never overheat. What kind of incredibly advanced technologies would that unleash?